Ever found yourself pondering over the basic concepts of chemistry? If so, you're not alone. Chemistry, the central science, bridges the gap between physics and biology and is a crucial part of understanding the world around us. It's a field that's as broad as it is deep, encompassing everything from the interactions between atoms to the properties of complex substances. Historically, scientists took a particular approach to understand matter, investigating its tiniest components to explain the larger world. They discovered laws of chemical combination, setting the groundwork for our understanding of chemical reactions. This journey into the intricate world of chemistry begins with Dalton's atomic theory, a cornerstone of modern science. It introduced the concept of atoms and molecules, the smallest units of chemical elements. As we delve deeper, we'll explore atomic and molecular masses, the mole concept, stoichiometry, and much more. So buckle up and get ready to dive into the fascinating world of atoms and molecules. Picture a world smaller than the eye can see, where elements, atoms, and molecules rule. Welcome to the world of Dalton's atomic theory, a cornerstone in the field of chemistry. In the early 19th century, a man named John Dalton proposed a theory that revolutionized how we perceive matter. He suggested that matter, in its most basic form, consists of tiny indivisible particles called atoms. These atoms, according to Dalton, are the building blocks of everything around us. This theory was groundbreaking because it proposed a tangible model to explain the interactions of matter. It gave us a way to understand why and how chemical reactions occur. Dalton's theory is like a map, guiding us through the complex terrain of chemical reactions. Now, let's delve a little deeper into the main components of this theory: elements, atoms, and molecules. An element is a substance that consists of only one type of atom. For instance, gold is an element because every atom in gold is a gold atom. Atoms, as we've already established, are the tiniest particles of an element. They're like the building blocks of an element. Each atom retains the properties of the element it belongs to. When atoms of the same or different elements combine, they form what we call a molecule. A molecule of water, for instance, consists of 2 hydrogen atoms and 1 oxygen atom. Dalton's atomic theory was the first to introduce these concepts. It gave us a new way of viewing the world, not as a collection of random objects, but as a composition of elements, atoms, and molecules. It helped us understand that the properties of matter depend on the type and arrangement of atoms. This theory is more than just a scientific concept. It's a lens through which we can view and make sense of the world around us. It's a testament to the fact that sometimes the smallest entities can have the most significant impact. Like a tiny universe, each atom plays a crucial role in the grand scheme of chemistry. So the next time you look around, remember that you're not just seeing objects, but a fascinating world of atoms interacting in remarkable ways. Imagine if we could weigh an atom. Sounds impossible, right? But in chemistry, we do just that. Atoms are the tiny building blocks of everything around us. They're so small that their masses are almost incomprehensible. But that doesn't stop chemists. In chemistry, we've developed ways to measure these incredibly light particles. This is what we call atomic mass, which is the mass of a single atom of an element. It's typically measured in atomic mass units, where 1 atomic mass unit, or AMU, is approximately equal to 1/12 the mass of a carbon-12 atom. Now you might be wondering, how do chemists measure something so small? Well, they don't actually weigh each atom on a tiny scale. Instead, they use a tool called a mass spectrometer, which measures how different atoms behave when exposed to magnetic fields. This gives us a relative measure of their masses. But what if we're dealing with molecules, which are groups of atoms bound together? That's where molecular mass comes in. The molecular mass of a substance is the sum of the atomic masses of all the atoms in a molecule of the substance. For example, water, or H2O, consists of 2 hydrogen atoms and 1 oxygen atom. So its molecular mass is the sum of the atomic masses of these atoms. In the world of chemistry, these tiny units of mass are incredibly important. They help us understand the fundamental properties of elements and compounds, predict how substances will react with each other, and even create new materials. So, The next time you think about the weight of something, remember that in the world of atoms and molecules, even the tiniest weights have a big impact. The scale may be minuscule, but the implications are huge. In the realm of the minuscule, even the smallest weights matter. Ever heard of the term mole outside of biology class? In chemistry, it has a whole different meaning. Now, let's dive into the fascinating world of moles and molar mass. In chemistry, a mole is not a small, burrowing mammal, but a standard scientific unit for measuring large quantities of very small entities such as atoms, molecules, or other specified particles. But why do chemists use moles? Well, trying to count individual atoms or molecules would be like trying to count every grain of sand on a beach. It's practically impossible. So instead, chemists use the mole, which is roughly equivalent to 6.022 times 10 raised to the 23rd power particles. This number, known as Avogadro's number, is extraordinarily large, but it's crucial for dealing with the minuscule sizes of atoms and molecules. And what about molar mass? Molar mass is the weight of 1 mole of a substance, usually expressed in grams per mole. It can be determined by adding up the atomic masses of every atom in a molecule. For instance, water's molar mass is 18 grams per mole, derived from 2 hydrogen atoms and 1 oxygen atom. Understanding the mole concept and molar mass is key to comprehending chemical reactions. These concepts allow chemists to predict how much of a reactant is needed for a reaction, or how much of a product will be produced. They enable precise calculations and predictions, which are essential in chemical experiments and industries. So, the next time you hear the term mole in a science context, remember it's not about a small creature, but a big concept that plays a vital role in understanding the microscopic world of atoms and molecules. With every mole, we unravel a new layer of the chemical world. What if we told you that cooking and chemistry have something in common? They both involve recipes, or as chemists call it, stoichiometry. Let's dive into the world of stoichiometry. It's a big word that sounds more complicated than it is. At its most basic level, stoichiometry is the math behind chemistry. It's the study of quantitative relationships between the amounts of reactants used and products formed in a chemical reaction. You could say it's like a perfectly balanced seesaw, where everything on one side equals everything on the other side. Here's a simple way of looking at it. Imagine you're baking a cake. The recipe calls for 2 eggs, 1 cup of sugar, and 2 cups of flour. Each of these ingredients represents a reactant. Mix them together, bake it at the right temperature, and voila! You have a cake. That's your product. The recipe, or the stoichiometry, guides you on how much of each reactant you need to get your desired product. Now, let's apply this to a chemical reaction. Consider the reaction of hydrogen with oxygen to form water. The balanced equation for this is 2 molecules of hydrogen react with 1 molecule of oxygen to produce 2 molecules of water. This is stoichiometry in action, guiding us on the quantities of reactants we need to produce a certain amount of product. But what if we want to calculate the amount of product formed from a given amount of reactant or vice versa? That's where calculations based on stoichiometry come in. These calculations involve using the balanced chemical equation and the concept of a mole to determine the amount of product or reactant. In essence, stoichiometry is all about balance. It's about understanding how much of one thing you need to react with another to get exactly what you want. It's a fundamental concept in chemistry that helps us predict outcomes of reactions, design new reactions, and even understand processes happening in our bodies. Stoichiometry, the recipe of chemistry, guiding us through each reaction. From atoms to moles, from masses to reactions, we've journeyed through the basics of chemistry. As we've seen, chemistry is a vast and diverse field, with a rich history and integral role in our daily lives. We've delved into Dalton's atomic theory, gaining insight into the building blocks of matter, the concept of elements, atoms, and molecules. We've explored atomic and molecular masses, understanding how these masses are critical in chemical reactions and compositions. Then, we ventured into the mole concept and molar mass, illuminating how they provide a bridge between the atomic and macroscopic worlds. Finally, we plunged into the realm of stoichiometry, linking the quantitative aspects of chemical reactions and providing a basis for calculations. Each of these concepts, while distinct, are intertwined, forming the fundamental framework of chemistry. Next time you ponder about the mysteries of the universe, remember, some of the answers lie in the world of chemistry.